My topic is about data hazards in computer architecture and how we can resolve them. First, let's look at the problem. A data hazard occurs when an instruction depends on the result of a previous instruction that hasn't completed yet. This is typically called a read after write hazard. For example, look at this code. The add instruction calculates S-lin, but it only writes the result back to the register file in the write back stage. However, the sub instruction needs S-lin immediately in its decode stage. Without any intervention, the sub instruction will have to wait or store for several cycles until S-lin is written, creating bubbles in the pipeline and wasting time. So, how do we fix it? The first hardware solution is forwarding, also known as bypassing. The key insight is that the result is actually ready before the write back stage. It's calculated in the ALU stage. Instead of waiting for the data to go all the way to the register file, we add extra connections in the data path to forward the result directly from the pipeline buffers to the next instruction. By doing this, the sub instruction can get the value of S-lin as soon as it's computed, allowing the pipeline to run without stalling. However, forwarding doesn't work for everything. We encounter a special case called the load use data hazard. Consider a load word instruction, followed immediately by an instruction that uses the loaded data. The data from memory is only available at the end of the memory stage, but the next instruction needs it at the beginning of the execute stage. We cannot forward data backward in time. Therefore, even with forwarding, we are forced to insert a bubble of one cycle. This reduces our performance as shown in the timing diagram. The setup will take more cycles to complete due to these bubbles. Since forwarding cannot completely solve the load use hazard, we turn to a software solution called reordering. Let's look at this C code example. In the unoptimized assembling code, we load T2 and immediately use it. We also load T4 and immediately use it. This creates an avoidable stores. According to the calculations, these executions take 13 cycles. To optimize this, the compiler can reorder the instructions. We can move the instruction load word T4 up to fail the source start after load word T2. This instruction is independent of the one around it, so it doesn't change the program's logic. By filling the bubble with useful work, we eliminate the stores. As you can see in the comparison, the optimized code finished in 11 cycles instead of 13. This demonstrates how smart compiler scheduling can significantly improve hardware efficiency. In conclusion, data hazards are a major challenge in pipeline. We use forwarding to solve most ALU to ALU hazards. For load use hazards, forwarding isn't enough, so we often fetch a store. Finally, we use code reordering to fill those stores with independent instructions, maximizing our throughput. Thank you for listening.